Bingham and his team go on to uncover 5 square miles of what are Inca ruins, dating back several centuries. Locals tell Bingham the site is called Machu Picchu.
The Inca are really well known for their incredible stonework, which is called ashlar masonry.
8,000 feet above sea level, stone walls cling to a near vertical mountainside. Tourists snap photos. Tour guides repeat the same story. The Inca built farming terraces here in the 1400S.
Pisac is the site of a ruined Inca fortress. It stands on a mountaintop over 3,500 meters above sea level.
That quote, S the version you've heard. That's what the postcards sell.But. But in 2025, ground-penetrating radar revealed something buried beneath those stones. Something nobody expected. A network of channels carved into solid granite. Drainage systems that modern engineers can't explain. And construction techniques that shouldn't exist without written blueprints or advanced surveying tools.Here, quote, S. What stops civil engineers cold? These terraces have survived 600 years of earthquakes and 80 inches of rain annually. Modern retaining walls, they fail in 50 to 100 years. Kenneth Wright, a hydraulic engineer with 35 years of experience, measured the system and said he'd never seen a better design. Even in million-dollar projects, the precision is 2 millimeters. Stones weighing over a ton, fitted tighter than a credit card's thickness. On a 60-degree slope, at oxygen-depleted altitude. Using copper tools that can't cut granite. The math doesn't work. The timeline has cracks, and beneath the lowest terrace, radar found something else. A chamber carved into bedrock that remains unexplored. Stay with us. What we're about to reveal challenges everything you thought you knew about ancient engineering. What the radar actually found. When Dominika Siczkowska from the University of Warsaw pointed her drone-mounted LiDAR scanner at Machu Picchu in 2024, she expected to map some hidden structures in the jungle nearby. What she didn't expect was what showed up beneath the terraces themselves. The scans revealed something remarkable. Below every visible terrace runs a network of underground channels. Not simple ditches, precisely carved pathways cut into granite bedrock. These channels vary in depth based on the local geology. Some are 2 feet deep, others go down 6 feet. Each one is angled at a specific gradient to move water efficiently without causing erosion. The discovery changed how archaeologists view the entire site. For over a century, researchers focused on the visible structures of the temples, palaces, and impressive stone walls. The terraces were seen as basic farming platforms, functional but simple.
Machu Picchu is a stunning example of the Inca's engineering feats. The Inca constructed Machu Picchu's palaces, temples, terraces, and infrastructure using stone.
The radar scans told a different story. A team from Peru's National University analyzed the data in 2025. They found that 60% of the construction effort at Machu Picchu went underground. Most visitors see the stone walls and impressive buildings above ground. They don't realize the real engineering miracle is buried beneath their feet. Kenneth Wright, a hydraulic engineer from Colorado, excavated the main plaza back in the 1990s. When his team dug down 9 feet, they discovered 4 distinct layers. 3 feet of rich topsoil at the top. Below that, sandy and gravelly soil for drainage. Then a layer of crushed white granite chips from construction waste was deliberately placed to filter water. At the very bottom, a structured drainage system made from larger stones, each one carefully positioned. This isn't random. Every layer serves a specific purpose. The topsoil grows crops and absorbs initial rainfall. The sandy layer filters water and prevents fine particles from clogging the system below. The granite chips create porous spaces that allow water to flow through while catching any remaining sediment. The bottom layer of larger stones moves water away from the foundation and into the main drainage channels. Wright, quote, ES team measured everything. They tracked how much water each layer could hold, how fast water moved through each section, how the layers worked together during heavy rain. The numbers showed something extraordinary. the system could handle rainfall that would overwhelm most modern drainage networks. Ground-penetrating radar surveys in 2025 confirmed something even more surprising. These underground systems are connected across the entire site. Water doesn't just drain from one terrace and disappear. It flows through an integrated network that moves water across the entire mountainside. When rain falls on the upper terraces, the system captures it, filters it through multiple layers, and directs it safely away from areas where buildings stand. The network includes main channels, secondary channels, and small connecting pathways. During heavy storms, water enters the system at hundreds of different points. It all flows downward, following carefully planned routes that prevent any single channel from becoming overwhelmed. The design prevents flooding, controls erosion, and keeps the terraces stable, even during Peru's intense rainy season. The most shocking discovery came when researchers tried to map all the drainage channels using artificial intelligence. They fed thousands of photographs and radar scans into the system. The AI analyzed stone shapes, channel angles, construction patterns, and material composition. After processing all this data, the AI identified 47 different construction techniques across the terrace system, 40-7 distinct methods. Some techniques appear nowhere else in the archaeological record. Others match methods used by different Andean cultures, separated by hundreds of miles and several centuries. A few show characteristics that researchers can't link to any known culture in the region. Why would one construction project use 47 different techniques? That's like building a modern house with bricks from Rome, wooden frames from Japan, and steel beams from America, all in the same structure. It doesn't make sense unless different groups of builders worked on Machu Picchu at different times. Or unless the builders had access to knowledge from multiple sources and deliberately chose the best technique for each specific location and purpose. The radar data also revealed something else. Beneath some of the visible terraces are older terrace foundations. These buried structures are oriented at different angles. They use similar drainage principles, but slightly different construction methods. It's as if someone built an earlier version of the terraces. Then later builders covered them and built new terraces on top, following the same sophisticated engineering approach, but adapting it to their own needs. The precision problem. Walk up to any terrace wall at Machu Picchu. Run your finger along the stones. You'll feel smooth surfaces fitting together so tightly that you can't slip a knife blade between them. This precision exists throughout the terraces, not just in a few showcase walls, but in virtually every section you examine. Each stone seems to have been shaped with a level of care that modern engineers find astonishing. It's not just that the stones fit, they fit in a way that creates an almost seamless surface, as if each one were part of a carefully orchestrated puzzle that has stood the test of centuries. In 2014, researchers from Kyoto University used 3D laser scanning to measure the stone joints. They discovered tolerances of less than 2 millimeters across hundreds of meters of terrace walls. Some of these stones weigh over a ton, yet each was cut and placed to align perfectly with its neighbors. The level of skill and consistency required is mind-boggling.
Machu Picchu is Peru's most famous tourist spot. By midday, around 700 tourists had already visited the site.
Especially considering the tools the Inca supposedly had at their disposal. Modern stonemasons still struggle to achieve this level of precision, even with diamond-tipped power saws, laser levels, and computer-aided design software. The Inca, in comparison, are said to have worked with nothing more than river rocks, bronze chisels, and sheer ingenuity. Bronze, with a hardness of just 3 on the Mohs scale, is far too soft to cut granite efficiently. Granite, the primary stone of these terraces, ranks between 6 and 7 in hardness. It's like trying to carve steel with a spoon. The metal wears away long before the rock does. So how did they manage it? Some recent studies suggest that the Inca may have used harder stones, like hematite or other abrasive minerals, to rough shape the granite. While this could explain the initial cutting, it doesn't fully account for the perfect fit. Achieving tolerances within 2 millimeters would require not only hard tools, but meticulous measurement, repeated testing, and incremental adjustments. A stone would be placed, checked, removed, reshaped, and checked again over and over until it fit perfectly. This process would have been incredibly time-consuming. Researchers from the University of California at Berkeley estimated that building the terraces alone, under ideal conditions with well-fed workers, good weather, and expert coordination, would require around 1,500 laborers working full-time for 15 years. But Machu Picchu is far from ideal. It sits in a cloud forest where it rains nearly 200 days a year. The terrain is steep and treacherous, and workers would have struggled with mud, slippery rocks, and low visibility most of the time. Actual conditions likely slowed progress considerably, making the achievement even more remarkable. And the precision goes beyond the surface. The stones interlock in 3 dimensions. The faces you see fit perfectly, but the sides, backs, and edges also connect with surrounding stones, creating a self-supporting structure. This design allows the walls to shift slightly during earthquakes and then settle back in place, a phenomenon engineers today call seismic damping, which wasn't formally studied until the 20th century. Did the Inca understand earthquake resistance and intentionally build it in? Or was it an accidental discovery? The consistent precision across hundreds of terrace walls strongly suggests intent. Random trial and error simply doesn't produce the same results again and again. Machu Picchu's terraces are more than construction. They are a testament to planning, skill, and an almost unimaginable understanding of stone engineering.
It was a surprise. In the depths of the Andes, the nearest town to the UNESCO World Heritage Site,
The water system that shouldn't work so well. Machu Picchu receives 76 inches of rain per year. That's more than twice what Chicago gets. All that water has to go somewhere. If it pools on the terraces, the soil becomes waterlogged. If it runs down the mountain in streams, it causes erosion. Either way, the terraces would fail. Kenneth Wright's team spent years studying how water moves through Machu Picchu. They found that the drainage system can handle extreme rainfall without any surface runoff. During Peru's wettest season, 3 inches of rain can fall in a single hour. The terraces absorb it all. Here's how the system works. Rainwater hits the terrace surface. Most of it soaks into the soil. The water that doesn't soak in flows to the edge of the terrace, where it enters drainage channels cut into the bedrock. These channels direct water to the main drain that runs through the center of Machu Picchu. The channels aren't uniform. They vary in depth and width depending on how much water they need to handle. Upper terraces receive less water, so their drainage channels are smaller. Lower terraces receive water from upper terraces, plus their own rainfall, so their channels are larger. The gradients are calculated precisely. Too steep and water flows too fast, causing erosion. Too flat and water moves too slowly, allowing sediment to build up and clog the channel. Wright's team measured the slopes and found they match modern engineering standards for optimal drainage. But here's the remarkable part. The drainage network is optimized. A team from Purdue University ran computer simulations testing thousands of different drainage configurations. They wanted to see if they could design something better than what exists at Machu Picchu. They couldn't. The existing system represents something close to an optimal solution. How do you achieve an optimal solution without computers? In modern engineering, optimization happens through iterative testing. You design a system, run simulations, see what fails, redesign and test again. Repeat hundreds or thousands of times until you find the best solution. The terraces at Machu Picchu appear to have been built for the first time. No trial and error. No multiple versions that got progressively better. Just an optimal design implemented once. Wright called this statistically improbable. In 35 years of civil engineering, he'd never seen a better agricultural drainage system. And he's analyzed systems that cost millions of dollars. The drainage system includes another clever feature. The Inca used construction waste as drainage material. When they cut stones for walls and buildings, they created chips and fragments of granite. Instead of throwing this waste away, they placed it in layers beneath the terraces. The granite chips create porous spaces that allow water to flow through while filtering out fine sediment. This recycling serves multiple purposes. It gets rid of waste, it creates effective drainage, and it uses materials already on site, reducing the need to transport additional resources up the mountain. That's efficient engineering. The timeline doesn't add up. According to standard archaeological records, Pachacuti Inca Yupanqui is credited with ordering the construction of Machu Picchu around 1450. By the time the Spanish conquered the last Inca strongholds in 1572, the site had been abandoned. That gives a maximum window of roughly 120 years for the construction, with most estimates suggesting that the main building phase lasted only 50 to 60 years. By any measure, that is an impressive achievement, but the timeline becomes puzzling when we examine the evidence more closely. Carbon dating has complicated the story. In 2020, organic material discovered beneath the terrace foundations returned dates as early as 1250. Almost 200 years before Pachacuti's reign. Initially, archaeologists suggested that these results could be explained by contamination. Perhaps older materials from previous occupations had been mixed with Inca-era construction debris, making the terraces appear older than they really are. This seemed plausible at first, and many researchers treated it as a minor anomaly, rather than a serious challenge to the established timeline. But then came the 2025 radar surveys, which revealed something that contamination alone cannot explain. Beneath the visible terraces lie older terrace foundations, oriented differently from the terraces above, yet built with the same sophisticated techniques. The drainage systems are identical. The precision stone fitting mirrors that of the terraces we can see today. These aren't random piles of rock, they are carefully engineered structures. Buried but fully functional, discovering these older terraces beneath the Inca constructions is like unearthing a smartphone buried beneath a Roman road. Something entirely out of place and impossible to ignore. It suggests one of two startling possibilities. Either the established timeline is wrong, or a civilization predating the Inca achieved a comparable level of engineering sophistication. Adding another layer of intrigue, Spanish chroniclers who documented Inca culture in the 1500s recorded that when they asked the Inca about the massive stone structures across the empire, the Inca claimed they didn't know who built them. According to these accounts, the stones were already in place when their ancestors arrived. For centuries, historians dismissed these statements as fanciful myths or exaggerations. But if we take the Inca at their word, it could mean they inherited these structures rather than constructed them themselves. This perspective helps solve several historical puzzles. It explains why the finest stonework appears primarily in foundations and load-bearing structures, while later additions often display less precision. It clarifies why oral traditions emphasize that the stones were already there. And it accounts for the disappearance of knowledge regarding precision stone construction following the Spanish conquest. Perhaps the Inca were skilled maintainers, capable of adapting and expanding inherited structures without fully understanding the principles behind the original engineering. They could preserve the terraces and build on existing foundations. But designing such a system from scratch may have been beyond their grasp, or at least knowledge they no longer possessed. If this scenario is accurate, Machu Picchu becomes not just a testament to Inca ingenuity, but also a link to a lost tradition of architectural mastery, hinting at a sophisticated understanding of stonework that predates even the most famous Inca rulers. What does this mean for history? The traditional story says the Inca built Machu Picchu in the mid-1400s as a royal estate for Pachacuti.
There's a story from 400 years ago about the end of the Inca Empire when the Spanish came in and took them over, that they took all of the king's gold and hid it in a place that is called Vilcabamba.
They used bronze tools, wooden levers, and human labor to move stones and carve terraces into the mountainside. The precision came from skilled workers and patient effort. The new evidence suggests this story is incomplete. The terraces show engineering sophistication that rivals modern civil engineering. The drainage system is optimized in ways that typically require computer modeling. The stone precision is consistent across hundreds of walls, not just a few showcase examples. And buried beneath the visible terraces are older structures from an earlier construction phase. Three possibilities emerge from this evidence. First possibility: the Inca were far more sophisticated than we've given them credit for. They developed advanced engineering knowledge without writing it down. They achieved precision without modern tools through techniques we haven't rediscovered. They designed optimal drainage systems through careful observation and generational learning. This is possible, but it requires us to believe they lost all this knowledge within a single generation after the Spanish arrival. Second possibility: the construction period was much longer than we thought. Maybe work started in 1250 instead of 1450. That gives 300 years of development instead of 50. More time allows for more experimentation, more learning, and more refinement. The buried terraces might be earlier versions that were later covered and improved. This explains the timeline, but doesn't explain why Spanish chroniclers never mentioned such a long construction period. Third possibility: the Inca inherited and modified an existing site. Earlier builders, possibly from a culture we don't have clear records of, created the foundations and basic terrace system. The Inca recognized the value of the site, added their own structures, and maintained the sophisticated drainage systems without fully understanding how they worked. This explains the variations in stone quality, the oral traditions claiming the stones were already there, and the rapid loss of knowledge after the Spanish conquest. None of these possibilities involve ancient aliens or lost advanced civilizations. They're all within the realm of human capability, but they do require us to revise our understanding of how technical knowledge develops and spreads. The buried chamber detected by radar in late 2025 might provide answers. It remains unexplored. Peruvian authorities haven't authorized excavation yet. What's inside could change everything we think we know about Machu Picchu's history.
Machu Picchu, of course, located in Peru, was named one of the new wonders of the world back in 2007 after receiving over 100 million votes in a global competition.
Modern engineers study ancient techniques. Today's civil engineers study Machu Picchu for practical reasons. The terraces have survived 600 years in conditions that destroy modern structures. That's valuable knowledge. Nicolas Estrada Mejia from Peru's Los Andes University has spent years analyzing why Inca walls survive earthquakes. He's found that the mortarless construction allows walls to dance during tremors. The stones shift slightly, absorb seismic energy, then settle back into place. Buildings with rigid mortar crack and fail. Buildings with flexible stone-to-stone contact survive. Modern architects are applying these lessons. In earthquake-prone regions, new buildings incorporate flexibility features inspired by Inca design. Base isolation systems, flexible joints, and energy-dissipating elements all work on similar principles to Inca masonry. The drainage systems offer lessons for sustainable construction. Modern storm drains often handle water by moving it quickly away from structures. Machu Picchu's system works differently. It slows water down, filters it, and distributes it safely across the landscape. This approach reduces erosion and prevents downstream flooding. Wright's research influenced modern water management practices. His analysis of Machu Picchu's drainage capacity showed that relatively simple systems can outperform complex modern infrastructure if designed with sufficient understanding of local conditions. The terrace construction technique is being studied for applications in slope stabilization. Many regions face landslide risks on steep terrain. The Inca approach of building terraces with integrated drainage prevents soil saturation that triggers landslides. Modern engineers are adapting these methods for hillside communities in landslide-prone areas. Perhaps most importantly, Machu Picchu demonstrates the value of building for longevity. Wright estimated that 60% of the construction effort went underground, into foundations and drainage that visitors never see. Modern construction typically prioritizes visible features over hidden infrastructure. Machu Picchu's 600-year survival suggests this approach is backwards. So where does this leave us? We have 700 terraces covering 12 acres of steep mountainside. Each one is a multi-laid law. layered engineering system built with precision that matches modern standards. We have an underground drainage network that has worked perfectly for 6 centuries. We have stone construction techniques that achieved millimeter-level tolerances using bronze tools. We have carbon dates suggesting construction earlier than the accepted timeline. We have buried terraces from an older phase. We have quality variations suggesting different builders across time. And we have oral traditions saying the Inca inherited their finest stonework rather than creating it. The standard explanation that the Inca built everything around 1450 using simple tools and human labor doesn't fit all the evidence anymore. That explanation worked when we only had surface-level observations. Now we have ground-penetrating radar, 3D laser scanning, and detailed engineering analysis. The more precisely we look, the more questions emerge. Whatever the truth is, whoever designed Machu Picchu's terraces understood hydrology, geology, and structural mechanics at a sophisticated level. They possessed knowledge that we're still trying to fully rediscover. The terraces are still there, still draining water perfectly, still resisting earthquakes, still holding their secrets. The question isn't whether these terraces are impressive. They clearly are. The question is, are we ready to revise our timeline of human achievement to account for what they represent? The buried chamber beneath the lowest terrace waits to be opened. What it contains might finally provide clear answers. Until then, the terraces of Machu Picchu stand as monuments to engineering skill that we're still learning to appreciate.